Hi guys, so we're going to be going through a Further Mechanics AS paper, which is from 2018, and hopefully we'll get this all done in one video. Okay, so always good to read this bit at the beginning, it's a good reminder. And it says, whenever you need a numerical value of g, take g as 9.8 and either use 2 or 3 significant figures throughout. A small ball of mass 0.3 kilograms is released from rest from a point 3.6 meters above the horizontal ground. It falls under gravity and hits the ground and rebounds vertically upwards. In the first impact with the ground, the ball receives an impulse of magnitude 4.2 newton seconds. The ball is modelled as a particle. Find the speed of the ball immediately after it first hits the ground. So there's a ball like this, it's falling down, it hits the ground with a certain speed, it bounces up with a certain speed, and it's going to come up to here, okay? I need to find out what is this speed going to be as it hits the ground. So for that first journey, and that first journey is going to be from here down to when it hits the ground, okay? I know some things about this. I know that if I'm taking downwards to be my positive direction, I know that it is starting from rest. I know that the distance it's traveling is 3.6 meters, and I know that the acceleration is 9.8. I'm not very happy with that U there. Well, it looks like an H. And it still looks like an H. I need to get better at using this tablet, I tell you. There we go. So what we need to do, we want to find out how fast does it hit the floor. So I'm trying to find out what v is equal to. Very clearly, you can see that they are connected by v squared equals u squared plus 2as. So u squared is 0 squared, don't know why I wrote that, plus 2 times 9.8 times 3.6. So v is equal to square root of that, so it's 2 times 9.8 times 3.6, square rooted is 8.4. So now we know that it receives an impulse of 4.2. So when it hits the floor, it receives an impulse in this direction. It previously was going at a speed of 8.4, and we know that it is going to rebound, different v this time though, and we want to find out what's this speed over here. Now we know that I equals m brackets v minus u, and in this case we're taking the direction of the impulse to be positive. And the impulse is 4.2. The mass is 0.3. V is the thing we're looking for. U is going in the opposite direction, so it's going to be taking away negative 8.4. So that is, if I divide both sides by 0.3, I get 14 equals V plus 8.4. If I then subtract the 8.4, I get that the speed with which it rebounds is 5.6. My laptop's getting a bit tired, I think. Kind of like me. And V equals 5.6. So the speed of the ball immediately after it first hits the ground is 5.6 meters per second. Wants us to find the kinetic energy lost by the ball as a result of the impact. So the kinetic energy lost is going to be the kinetic energy before the impact minus the kinetic energy that it has after. So it's going to be a half times the mass times the velocity squared minus a half times the mass times the speed squared, I should have said, rather than velocity. I'm just going to type that in a calculator. So that's 5.88 joules. No rounding required because we've already got it with 3 numbers. Okay, easy first question. Question 2. When I see this kind of question, I think, it's probably going to be a work energy power sort of question. So figure 1 shows a ramp inclined at an angle theta to the horizontal, where sine theta is 2/7. A parcel of mass 4 kilograms is projected with speed 5 meters per second from a point A on the ramp. Okay, it's clearly going to be going up the ramp because I've got B there. So it's been given a speed of 5 and it's got a mass of 4 kilograms. I'm just going to add in that weight of 4g there. What else does it say? The particle moves along the line of greatest slope of the ramp and first comes to instantaneous rest at B. So here it has got no speed at all, but it's obviously still got its weight and some other forces too. The parcel is modelled as a particle. The total resistance to the motion of the particle from non-gravitational forces is modelled as a constant force of magnitude r newtons. So there's a resistant force. Normally we say that r is the normal reaction, but there is an extra resistant force that is going on here. Use the work energy principle to show that r equals 8.8. Okay, so we've got to think about what energy it's got at this stage in the bank, like I like to say, and then we're going to think, how does it spend that energy for it to get all the way up to B? Well, it looks like it's got some kinetic energy, and that kinetic energy is completely spent. It is spent on two things. One, increasing its height, so it's some potential energy, some gravitational potential energy. The other thing it's spent on is overcoming friction, this resistant force. So I'm just going to write that down. The kinetic energy at A is going to be spent on two things. It's going to be spent on converting it to the gravitational potential energy at B, and it's going to be spent on the work done against the resistance, but I'm still going to call it the friction here. So the kinetic energy at A is a half times the mass times the speed squared. Then we're going to work out the gravitational potential energy at B. Well, if we call this the 0 point where it started, and we know that it's going 2.5 meters along, and we know that this is theta, and we want to find out what the height is, well, the height is 2.5 sine theta. Thinking of trig there, okay? So the height is that. What have I put? So we get mg multiplied by the height, which is 2.5 sine theta. And the work done against friction is just the force multiplied by the distance that it travels. So this is 50. This is 4g times 2.5. Sine theta is 2 over 7, and that's 2.5r. So I've got 4 times 9.8 times 2.5 times 2 over 7, which is 28. So I get 50 equals 28 plus 2.5r, and I'm just going to solve that equation by taking away 28 and dividing by 2.5, and we get that r is equal to 8.8 newtons. Okay, after coming to instantaneous rest at B, the particle slides back down the ramp. The total resistance to the motion of the particle is modelled as a constant force of magnitude 8.8. Find the speed of the parcel at the instant it returns to A. Suggest two improvements that could be made to the model. Okay. So now we're thinking of the journey in reverse, and we need to think about what energy it has and how it's being spent. It's got no kinetic energy up here, but it has got gravitational potential energy, and it is going to be spent on kinetic energy. It's going to be spent converting to kinetic energy and overcoming friction. Now, it's not going to get to 5 when it comes here, because the energy that it had at 5 meters per second has been spent on the friction, and it's going to be spent again on the friction. So I'm expecting an answer that is less than 5. So now I'm going to say that the gravitational potential energy at B is going to be converted into kinetic energy at A plus the work done against friction. Being lazy there. The gravitational potential energy at B was this bit, which was 28. The kinetic energy at A is a half times the mass times the speed squared. That's the thing I'm trying to find, the speed. And the work done against friction is 2.5 multiplied by the force, which is 8.8. So 2.5 times 8.8 is 22. So that is 28. Take away 22 is equal to 2v squared. So that is 6 over 2, which is 3. So 3 is equal to v squared. So v is equal to the square root of 3, which is 1.73 meters per second. And that's obviously to 3 significant figures. That's just solving the equation there if you didn't follow what I was doing. So it had all this potential energy because it was high up. As it slid down, that energy was converted into the kinetic energy that it had at A and overcoming some of the friction that we had there. 2 improvements that could be made to the model. Well, let's see some things that we've got here. First of all, the forces has been modelled as a constant force of magnitude r newtons. So the resistant force, instead of being constant, could vary, and the thing it would vary with speed. That's a good improvement. The other thing that's happened is that we have taken the model as particles. So we could take in the dimensions of the particle. So we could take the dimensions of the parcel into account. Now, I perhaps wouldn't say about air resistance here, because they've talked about the other resistant forces. They've talked about non-gravitational forces, which would include air resistance, the total resistances. So they actually have taken into account some air resistance here, which is why you should not say air resistance, even though it's talking about a particle. Okay, let's double check this. We didn't check the first one, did we? The first one we got correct. We got 8.4, 5.6, and 5.88 joules. So we did get that one correct. Let's have a look at question 2. We did come up with R equals 8.8. And we've got 1.7 or 1.73 for this stage that we've got here. And let's see what part C is. The improvements could be having variable resistance, and do not model the particle as a parcel, so that we can consider the dimensions, or a couple of other things there that you might like to read. So you can't talk about air resistance or friction because they're already mentioned, like I said. Okay, so we've got question 3, 4, and 5. I think we can do this all in one video. Question 3, if you're in my group, you haven't actually studied this bit yet, but you'll be able to do it quite soon. So for question 3a, a van of mass 750 kilograms is moving along a straight horizontal road. At the instant when the van is moving at v meters per second, the resistance to the motion of the van is modelled as a force of lambda v, where lambda is a constant. Just going to do a quick sketch of this. So there's my van. It's 750 G. It's got a normal reaction. It's got lambda v as a resisting force, and we've got some driving force here, which I like to call the letter D for the driving force. The engine of the van is working at a constant rate of 18 kilowatts. So we know that power is equal to 18,000. We also know that power is equal to the driving force F, or the driving force D in this case, multiplied by the speed, or FV, but in my case it's D. So, at the instant when v equals 15, the acceleration is 0.6. Well, if v is equal to 15, let's find out what d is equal to. So we get 18,000 is the power, is equal to 15d. So d is equal to 18,000 divided by 15. D is equal to 1,200. Now, I am going to resolve in this direction using F equals ma. So D minus lambda v, that's my resultant force, is equal to the mass multiplied by the acceleration, which they've told me is 0.6. So that's 1,200 minus lambda v, well v is 15, so that's 15 lambda, equals 750 times 0.6, which is 450. Solving this equation, that's 1,200 minus 450 divided by 15, lambda equals 50. Okay. The van now moves up a straight road inclined at an angle to the horizontal, where sine alpha equals 1 over 15. Let's get my diagram begun. At the instant when the van is moving at v meters per second, the resistance to the motion of the van from non-gravitational forces is modelled as a force of 50v. Well, that's what we found out earlier. When the engine of the van is now working at a constant rate of 12 kilowatts, the van is moving at a constant speed v. Okay, so here's my van. We've got a driving force. We've got a force coming back of 50v. We've got a normal reaction, and we've got the weight coming down, which is 750 G. Now, the weight needs to be split up. Let's get a new colour. And the weight is going to be split into this force and this force. And the one going downwards is the one I'm interested in, which is going to be 750 G sine that's theta, that's theta, 750g sine theta. So if I were to redraw this diagram but kind of flattened out, we've got r going up, d going to the right, 50v going to the left, 750g sine theta, and coming down 750g cos theta. But we're not going to need this up and down bit. Now, because it has constant speed, we know that it is in equilibrium. Equilibrium, because of constant speed. In other words, we know that d equals 50v plus 750g sine theta. And there's a few other things we know. We know that the power is equal to 12 kilowatts. So we know that power is 12,000. In other words, 12,000 is equal to the driving force multiplied by the speed. So the driving force is 12,000 over v. This little v can now change to a capital V, and we have 750g sine theta. So that's 750g, and sine theta is 1 over 15, I believe. Yep. I think it's alpha. I've used theta, but I wouldn't worry. So that's 750 times 9.8 divided by 15. That's 490. So 12,000 over v equals 50v plus 490. This is a quadratic if you multiply through by v. I'm going to put it all on one side. So that's 50v squared plus 490v minus 12,000. I'm just going to use my equation solver for this because it just makes sense. So that is going to be 50, 490 and minus 12,000. And you come up with that v is equal to 11.3 meters per second, or minus 21.14 meters per second. But obviously v has got to be greater than 0, so v equals 11.3 meters per second. That one's not going to be valid. Does that seem sensible? Yeah, it was moving at 15 meters per second, so seems kind of reasonable. Let's have a look at the mark scheme. So we got that one. We knew that we'd got that correct. They've used F instead of D, whatever you want to do. And you come up with 11.3. So it's like quadratic. They've got it here, but you can just, they've got the quadratic formula. You can just use a calculator. Okay. Question 4. I love these kind of questions. I think there's actually only 4. Great. Okay, a particle P of mass 3m is moving in a straight line on a smooth horizontal floor. A particle Q of mass 5m is moving in the opposite direction to P. So as soon as I know some information on it, this one is 3m and it's P. This one is 5m and it's Q, and they're moving in opposite directions. Immediately before the collision, the speed of P is 2u, and the speed of Q is u. The coefficient of restitution between them is e. Okay, I always call them x and y. It's just the habit I'm in. So I'm going to call that one x, and I'm going to call that one y, and I just have them going to the right. So there's 2 things you can do. You can do PCLM. So I'm going to do this times this, which is 6mu. This one's going to be negative because of the u going to the left this time, minus 5mu. And that's equal to 3mx plus 5my. So I can cancel out the m from everything because there's m's in all of them. 6u take away 5u is just u. So u equals 3x plus 5y. Then we're going to do Newton's law of restitution, which is the speed of separation, y minus x, over the speed of approach, which is those two added, which is 3u, and that's equal to e. So you get that y minus x equals 3eu, and we want to find out the speed of q. We want to find out what y is, so we need to make x the subject. So it will be y minus 3eu equals x. So I'm going to take this and I'm going to substitute it into number 2. So let's substitute 1 into 2. So u equals 3y minus 3eu, that's what x is, plus 5y. U equals 3y minus 9eu plus 5y. So that is u plus 9eu equals 8y. Factorize the u, divide by 8, and we get what y is equal to, which is u over 8, 9e plus 1. Let's just write it in the way they wanted it. U over 8, 9e plus 1. Find the range of values for e for which the direction of motion of p is not changed as a result of the collision. So if we want this to be not changed, I want x to be positive. So I better find out what x actually is. So that was part A of the question. Here is part B. Now we know that x is equal to y minus 3eu, which is going to be 9 over 8 eu plus u over 8 minus 3 eu. So I'm going to do 9 over 8 eu minus 3. 9 over 8 minus 3 is minus 15 over 8. So I've got u over 8 minus 15 over 8 eu. I'm going to factorize the u over 8 out, which is 1 minus 15e. Now, we just said this earlier, I want x to be greater than 0. If x is greater than 0, it means it is still going to the right. If it was less than 0, it would have flipped and been going to the left. So that means I want u over 8, 1 minus 15e to be greater than 0, which means I want 1 minus 15e to be greater than 0, or e to be less than 1 over 15. But remember, it's also got to be greater than or equal to 0. I'm just going to quickly look at the mark scheme here just to check that we've got part B right, just to see we're on the right track. Yep, so E is between 0 and 1 over 15 that we have. Just wanted to check that before we went much further into this question. This is where things get interesting. When P and Q collide, they are at a distance d from a smooth fixed vertical wall, which is perpendicular to the direction of motion. After the collision with P, particle Q collides directly with the wall and rebounds, so there is a second collision between P and Q. This second collision takes place at a distance x from the wall. Given that E equals 1 over 18, and the coefficient of restitution between Q and the wall is a third, find x in terms of d. Okay, I've done some videos on these before, so hopefully you'll be alright with this. First of all, they've told us that E is equal to 1 over 18, so really quickly I want to work out what x is equal to and what y is equal to. Notice that 1 over 18 is in this range, so actually P is still travelling towards the right. So we have u over 8, 1 minus 15 multiplied by e, which is 1 over 18. So let's just find out what this speed is. It's going to be so much easier than working with e. So that's 1 minus 15 over 18, which is a sixth, and divide that by 8. So we have u over 48. And y is u over 8, 9e plus 1. So it's u over 8, 9 times 1 over 18 plus 1. So that's 9 over 18 plus 1 and divided by 8 as well. So you get 3u over 16. Okay, let's think about what's happening here. I'll do the diagram a little bit smaller. So they have just collided. There's then the bit where Q comes to the wall and bounces back. And then the third bit is when they have collided again. So at this point, Q is travelling to the right with speed 3u over 16. And Q is travelling to the right with speed u over 48. Now it hits the wall with speed 3u over 16, but it's going to bounce back, and because E is 1/3 for the wall, it's going to bounce back with a third of that speed. So all I need to very quickly do is a third of 3u over 16, which is clearly just u over 16. So it's now coming in this direction at u over 16, and P is still travelling to the right with speed u over 48. Now we need to work out, I think, what x is in terms of d, and x, if I make this right, is the distance of the second collision from the wall. So this distance here is x, and this overall distance to the wall, well, I've gone way too far there, is d. Okay, so there's a couple of different ways we can think about this. There's some journeys. I'm going to consider P. And I need to know certain things about it. I need to know the speed that it travels, the speed it's travelling at, the distance that it's travelling, and then I can work out what the time is. Well, the speed is u over 48. And the distance it's travelling from here to this collision point, well, if this is d and this is x, the distance it's travelling is d minus x. And I'm going to call that time 1 t1. Now, I have to always do this for some reason. My time is distance over speed. So it is d minus x over u over 48, which I'm going to rearrange as 48, multiplying the top and bottom by 48, 48d minus x over u. That is the amount of time that P is travelling. I'm now going to consider Q in two journeys. I'm going to consider Q from here to the wall. Consider Q, first collision to the wall. And I know that the speed of Q is 3u over 16. The distance to the wall is d, and the time I'm just going to call t2. And t2 is equal to the distance divided by 3u over 16. Multiplying the top and bottom by 16, I get 16d over 3u. That's what time 1 is. Sorry, time 1 is for P to go from here to this collision. Time 2 is for Q to go from here to this bit. And then time 3 is going to be for it to go from here to here. And then we're going to try and think how all those times connect together. So I should say first collision. And now I'm going to consider Q, and this is for the second, this is for the wall to the second collision. This time, the speed has changed. The speed is now u over 16. We worked that out over here. The distance that it's travelling this time is just x, because it's travelling from here to this second collision. And the time, I'm going to call it t3. Now t3 is going to be x over u over 16, multiply the top and bottom by 16, and you get 16x over u. Now, the amount of time that P is travelling is the same amount of time that Q travels in these two journeys. In other words, the connection between T1, T2 and T3 is that T1 is equal to T2 plus T3. So, T1 is 48d minus x over u. T2 is 16d over 3u. And T3 is 16x over u. Well, I can multiply everything by u and get rid of it. I can then expand these brackets, so I get 48d minus 48x equals 16 over 3d plus 16x. And we want to find out what x is equal to. So I'm going to rearrange this. I get 48d minus 16 over 3, which is 128 over 3. And that is equal to 64x. So if I divide both sides by 64, I get that x is equal to 2/3 d. pretty tricky question, but they love this kind of one, so you better learn how to do it. And you can see some of my videos. If you go to my collisions in one dimension playlist for further mechanics, you can see lots more questions that are like this. Let's check we got it right. X is 2/3 D, and here's the strategy. We've got the total time for Q and the total time for P. Make them equal to each other, and away you go. Pretty tough question. I'm going to leave it there. I've been doing a lot of videos today. I hope it went all right for you guys, and I'll speak to you soon.